Alright guys, I want to take a little bit of time to talk through some of the questions that you had for your homework tonight, mostly the conceptual ones with the PV diagrams, but we'll also do a problem as well. You're welcome to fast forward through if you just want to skip up to the answers, or you can listen to the explanations as we go. Alright, so this is the first one. We have 4 different processes. We've got process 1 going straight up, process 2 which goes up and then to the right, so increasing pressure then increasing volume. We have process 3 which goes diagonally, so changing pressure and volume at the same time. And then we have number 4 which is isobaric, only changing the volume. Alright, so we're going to look at ranking these from the greatest to the smallest amount of heat that are gained during each of the processes. Okay, so note that we do have 2 isotherms. Okay, we know that this one is a higher temperature, so I'm going to label that a high temperature and this the low temperature. Okay, that'll be helpful. And let's just go through and look at each of the following pieces. Okay, we know that the internal energy is equal to the heat plus the work. Now, since the internal energy is always going from one temperature to the other, that means the internal energy is going to be the same for all of these processes. That means that the heat will be directly related to the work. Okay, so we're looking for the heat gained, so we're looking for positive heat, and so the one with the most heat gained is going to be the one that has the lowest amount of work. Alright, the one that has the highest amount of work obviously doesn't need to gain as much heat. So we're looking for a low work, which means that either a 0 work, or it could even be negative. And a negative work, remember, is that your object is doing work on the outside. You'll notice that with the exception of process 1 goes straight up, there's no volume change, which means for this one the work is going to be 0. Okay, we did talk about that work is equal to pressure, negative pressure times the change in volume. So if there's no change in volume, there can't be any work occurring. So number 1, the work is 0. Let's look at 2, 3, and 4. You'll notice that they all move to the right, which means an increase in volume. An increase in volume is going to mean negative work being done. So the more negative work that's being done, the larger that the heat added will have to be. Okay, so let's look at which one gains the most, or which one is doing the most work. Now, work is gained by P times V. You can do that by actually looking at the pressures and doing it mathematically, but since 2 and 3 have changing pressures, then that's going to make it a little bit difficult. So what we can do is, instead of calculating it, we can just look at the area under the curve. And so if you look at process 4, there is my area for process 4. Alright, we're going to change our color. And so now we'll do process 3. Process 3, process 3 goes like this. Okay, so there's process 3. And then process 2 looks like it's a little bit bigger than 3. So the largest area, just by glancing at it, is 4. That means that the most work was done in number 4. And since that's a negative amount of work, that means it's going to have the most heat. So Q4 is going to have to be the biggest. The next largest amount of work is number 2, right? Because that's going to have the whole rectangle. 3 is a little bit smaller. So Q4 will have to be bigger than Q2, which will have to be bigger than Q3, and then that will have to be bigger than Q1 because Q1 is no work at all. Alright, so there you go. That's the answer to that question. Alright, let's move on to the second question. Okay, given the PV diagram below, identify whether work and heat are positive, negative, or 0, and then using words and pictures, identify how each step could physically be carried out. Alright, so let's start just at a random place. We'll start right here, and then we'll go over. Now, in this situation, you can look at it, and we can say, okay, it's isobaric. The pressure is staying the same. the volume is increasing. Okay, so there's a couple of different ways to do it. One is to think of the isotherms and knowing that as you go to the right, you're going to be heating up. Okay, so an increase in heat means that you're going, or sorry, an increase in temperature means that you're going to have an increase in internal energy, right? The other way to look at it is to do your PV equals nRT and understand that if the pressure is constant and the moles in the R are constant, then you're going to end up with V over T equals V2 over T2, which means that if the volume is increasing, the temperature also will have to increase. If this one goes up, this one has to go up. All right, so we know that the internal energy there is going to be positive. All right, the change in internal energy. Now we need the work and the heat. Since we have a positive amount of work being done, right, or sorry, a negative amount because the volume is decreasing, so this will be negative. The volume is increasing. That means the gas has to be doing work, so that'll be a negative amount of work. Now the only way that delta U can end up being Q plus W, if W is negative and delta U is positive, that means Q will have to be positive for this section. Okay, so increasing volume means that work is being done by the gas, which means it's doing the work will be negative, and so the heat will have to be positive. All right, let's look at the next step right here. Okay, now this one, again, you can remember the isotherms. This is going to be going to a cooler isotherm, which means it's losing, the temperature will be lower, so your delta U here should be negative. All right. Now that's going to be helpful with the work in the Q. You could also look at this by saying, okay, with PV and RT, if my volume remains constant, the moles in the R are also constant, then I'm going to get a similar P over T, similar to this one with the volume and the temperature. So if the pressure goes down, the temperature is going to have to go down. If the temperature goes down, we're losing internal energy. Now the work, since the volume is not changing, the work is going to have to be 0. So since the work is 0, if internal energy is negative, then the heat is going to have to be negative. It's going to have to lose heat. All right. Now the last one is adiabatic. All right. So delta U, W, and Q. I know it doesn't ask for delta U here, but obviously that's something that's been helpful to us so far. Delta U is a little bit more difficult. We know that Q is going to be 0. All right. Now when we consider the rest of it, what we'll have to do is consider what would happen with our PV and T. We know that the pressure is going to be increasing, the volume is going to be decreasing, so that's going to make it a little bit difficult to figure out what's going to happen to our temperature there, right? You can go ahead and put those numbers straight into PV and RT, right? If the N and the R are constant, that means that PV over T is going to have to equal to PV over T. So we can go ahead and look at that. If you know that the isotherm is always less steep than the adiabatic, then you know that this is going to be gaining temperature, which means that you're going to have a positive U. Also, you can look at the work. Since it's going this way, right, the volume is decreasing. If the volume is decreasing, that means work is being done on your system, and so work has to be positive, which means that you have a positive change in internal energy. You could also put these numbers in, put in the 500, the 100, the 1, and make an estimate for that one, and put in those numbers, and you could figure it out that way as well, and you would find that the temperature has to go up in this situation. All right, so that's that. Now the second part says, using words and pictures, can we identify how each step could physically be carried out? I'm going to go ahead and start in the same place. So I have a given pressure, and I want to increase the volume without changing the pressure. All right, we know that we have to add heat, so I'm going to take a cylinder, right, and we're going to put a piston on top of it, and we're going to put some amount of mass on it, which is going to be exerting a force on the piston. This force is going to be constant, and since pressure is force over area, and the force and the area are both constant, that means the pressure will be constant. The pressure inside is going to have to equalize with this. If this has a higher pressure, then it's going to push down until the stuff inside matches it. If this has a lighter pressure, then the opposite will happen. Okay? So now I know I'm putting heat into it, and so by putting a little fire underneath here, here's my logs, fire, that's going to put heat into it. That will keep the pressure the same, but the piston moving will allow it to change volume. Alright, so that's the first step. So now I've heated it up. The volume has changed. Still the same pressure because I still have the same mass on it. Okay, so I put the heat in. Now I'm on to the next step. So the next step, I understand, the temperature has to be able to go down, the volume has to remain constant, and I have to lose heat. Alright? So what's going to happen here is I want to keep the volume the same, and so I'm going to put a little pin in. We've done examples with that. You could glue it or something, but you want to fix the piston in place so that the volume doesn't change. Now if you want, you can just sit and wait, or you can put ice cubes on the outside or something like that to help the heat transfer go from inside to outside, right? Depending on what the temperature is inside and what your material is, you may have to put something out there to encourage that heat transfer. Alright, so that will allow the volume to stay the same. The pressure will decrease because there's heat going out and the temperature is decreasing. The internal energy is decreasing. Now this last step is one of the harder ones. We now need it to go back to the original pressure, back to the original volume, adiabatically. Now you can do this a couple of different ways. You can put it inside of a heat reservoir and make sure that the temperature stays constant and increase the pressure and change those types of things. But probably the easiest way to do it is to pull this pin out and very quickly push it back down to its original volume. Okay, by doing that with a very quick instantaneous change, there won't be time for heat transfer. Everything will automatically revert back to your ideal gas law and quickly change the pressure, volume, and temperature. And so that will be something that will be almost instantaneous, whereas the heat transfer requires time for the heat to go through the side, transfer to the ice, right? And so that's probably what you could do for that last step, unless you want to do some other thing with a heat reservoir and holding it at the same temperature. Alright, so there you go. There's conceptual example number 2. Now I am going to do one mathematical example just for the heck of it. In this process below, we're going to find Q. Alright, so now in order to find Q, really we have a couple of possibilities, but there's a couple of ways to do it, I guess, but we know that the internal energy is equal to 5 over 2 times nRT, right? So that's the internal energy of a diatomic gas. Now since that's the internal energy of the diatomic gas, then we can use that to be able to solve for the heat. Okay? So first we'll get the internal energy by using the 5/2 nRT by finding the temperature at these two positions, right? You can use PV equals nRT, and you can solve for the temperature at position A, and you can solve for the temperature at position B. Now I'm not going to take time to do that on this video because I'm running out of time, but you can get those two temperatures, temperature A and temperature B, which then you can plug in and find the internal energy at A, and you can find the internal energy at B. Once you have the internal energies at A and B, you can then do internal B minus internal A, which will give you the change in internal energy. Okay? Once we have the change in internal energy, you know that the change in internal energy is equal to Q plus W. So you now have the change in internal energy because you found the temperatures and you calculated that. Keep in mind, I used 5/2 very quickly, but that's because it's a diatomic gas. Okay? we have the pressures, we have the volumes, we have the number of moles. You know R is a constant, so that should be fairly straightforward. Once you have this, then all we need to do is find out the work. The work, again, is going to be equal to the area. Okay, now if it's a constant change like this one is, you can actually use the average pressure, right? We have talked about in class that work equals negative pressure times a change in volume. This equation only works for a constant or average pressure. So in this case, you could use that average pressure of 2 atmospheres, or you can use you can solve for the area underneath the curve. That is also fine. One thing to be sure of is you do have it in centimeters cubed here, which needs to be turned into meters cubed, right? And so you should do some type of conversion, getting from centimeters cubed to meters cubed. So that would be 1 centimeters cubed and then 0.00001 meters cubed, or you could do 1,000,000 centimeters cubed over 1 meter cubed, right? You can do that as well. And then you also need to turn the atmospheres into pascals. Alright, so that would be 1 atmosphere is approximately equal to 100,000 pascals. Alright, so I'm not going to go through and work the rest of it. I think that with those ideas you should be able to finish it up. So I wish you luck, and I hope that it works out. So I will go on and maybe talk to you in another video. Talk to you later.